Welcome to this new video series on how to learn particle physics. In this series, I will be talking about the right way to approach particle physics, from understanding the core ideas to exploring the mathematical foundations and reviewing some of the best books that can guide your learning journey. I will be covering several important texts, discussing how they are structured, what they emphasize, and which one fits your level of preparation the best. So by the end of this series, you will have a clear roadmap, not just of what to study, but how to think like a particle physicist. My name is Shaunak and you are watching this video on my channel, Physics for Students. Welcome to part 1 on how to learn particle physics. Well, before we go ahead and review the books, methods and the concept, first let us understand briefly and quickly what is particle physics. Well, particle physics is basically nothing but what explores the basic constituents of the universe. Particle physics explore the most basic constituents of the universe, particles like quarks, leptons and bosons, which together form all matter of forces that we observe. And this is something, it is the science of uncovering what everything is made of, and this is written in what is called the Standard Model. This together form all the matter and forces that we observe, the way components unified under what is called the Standard Model of particle physics, the theory that best describes the subatomic world. Now, you also need to understand that these tiny particles which we see in the Standard Model or otherwise, they interact through fundamental forces. And these fundamental forces are, first of all, gravity attracts all objects with mass, discovered by Newton. The strength is the weakest of all the three forces and its range is infinite but gets weaker with distance. The second comes what is called the strong force. It is called strong because it holds protons and neutrons together inside the nucleus. Strength is strongest of all forces. However, the range is very short, around 1 femtometer. The third comes what is called the weak force, which is responsible for all kinds of radioactive decay and particle transformations. Well, the strength is stronger than gravity but weaker than electromagnetism, and the range is extremely short, around 10 to the power minus 18 meters. Then comes electromagnetism. It acts between charged particles that can attract or repel. As far as the strength is concerned, it is much stronger than gravity and the range is infinite. Now, if we go further, we understand that chemistry studies atoms and nuclei. Particle physics further goes. It breaks down protons and neutrons into what are called quarks and gluons, revealing an even deeper structure of reality. It shows that everything, no matter how complex, is built from few of the fundamental ingredients. So the basic idea is that even the tiniest things we once thought to be very fundamental have further deeper structures, and this lies at the heart of particle physics. However, the notion and the basic idea of particle physics over the period of time and human intelligence have changed. Now, particle physics or the particles are not considered as particles. These are also not considered as analogous to what we call planets moving around the center of something. Here the electrons, protons and neutrons were thought to be rotating around a single nucleus, but now they are considered to be fields. So for all these fields, for example, electron, we have an electron field. For protons, we have a proton field. For photons, even we have a photon field. And protons are not exactly fundamental particles, so we further divide it in what is called a quark field. The photons also have a photon field. The gluons have a gluon field. And the most important discovery, the Higgs, also have a Higgs field. So at every point of time in space, you can think of a tiny number, a tiny arrow which is pointing, and although you cannot see it with your own eyes, but it is still there. And these are basically called fields, and they form the heart of what is called the quantum field theory. Well, the Standard Model unifies all the known fundamental particles, I would say, except gravity, obviously, under a single mathematical structure, and it predicts what we just saw, the existence of the particles called Higgs boson, whose discovery in 2012 confirmed a major missing piece of this theory. Particle physicists use giant accelerators which are called LHC or Large Hadron Colliders, and which they smash particles together at nearly approaching the speed of light. So as a result, these collisions recreate the energy conditions just which was allowed during the Big Bang, giving or allowing the scientists to observe new particles which might have emerged and interacted right at the beginning during the early universe. So from the standard model, which houses all the important information about particles, accompanied with Large Hadron Collider, which gives us a hint maybe what are the particles and situation which predicted in the early universe. From here what we can say that this particle physics acts as a kind of a bridge. It bridges cosmology and it connects this microworld of quarks with the world of galaxies. It helps us to understand not only early universe but the dominance of matter over antimatter and the nature of dark matter and dark energy which makes up the cosmos. Now, despite its success, which is called the standard model of particle physics, many mysteries are unresolved. There are certain things which are not solved, for example, gravity, dark matter, neutrino masses, and unification. Theories like supersymmetry, string theory, and quantum gravity aim to go beyond it, searching for a deeper, more elegant framework to understand the nature of reality. Well, this actually gives you a kind of an understanding, a bird's eye view on what is called particle physics. And now we venture forward in understanding how to learn particle physics. Well, learning particle physics, is it all about books, recommendations, links, videos? Well, I would say no. What it requires is basically building up the foundation. So in order to build up a foundation, first, as every physics theory demands, you need to start with classical physics, quantum mechanics, and special theory of relativity. There cannot be any kind of a consideration or any kind of an adjustment to that. These are the languages that particle physics speaks. You cannot jump into field theory without understand how particles move, interact, and they transform in space and time. The second thing obviously comes is your mathematical skills. So mathematics, as you understand the grammar of physics, so you need to have an understanding of linear algebra, calculus, complex numbers, and further, which I will discuss in today's video. So not these are abstract mathematics, but they are tools that explain how particles and fields behave. Also, importantly, you have to take a step-by-step approach. So do not try to grasp everything at one go. I would recommend please start with some introductory concept like standard model, basic quantum ideas, symmetry, and then slowly gradually move towards quantum field theory, Feynman diagram, and gauge theories. Also, you have to couple your learning with what is called theory and experiment, because every discovery in particle physics, from the electron to Higgs boson, actually comes from experiments. So you really need to have an idea of what are those experiments, read the journals, articles, and find out what are the recent discoveries so that your learning on particle physics is much more profound. Well, I would also like to recommend you a few more. Number one is to use visual aids and conceptual ideas. Particle physics might feel abstract. Feynman diagrams, symmetry charts, field visualizations, these are important to form an intuitive picture of what is happening beneath the math. I would recommend you to follow certain modern research papers considering CERN updates, neutrino experiment, and cosmological results. The reason is that they show how particle physics is a living, evolving science, not just a theory, but a continuous exploration. Also, there is a point on solving problems continuously, because until and unless you work out problems, for example, calculating decay rates, scattering amplitudes, or symmetry transformation, you cannot come to truly understand those things. Hence, particle physics is best understood by learning and by doing, not just by reading. Hence, all these things comes to a next question. What tools or how do we actually need to learn it? And for that, we come to the next part of our video, where I would be discussing about the mathematical prerequisites which are required for particle physics. Now, if I talk of the mathematics, I would take it in a kind of a table structure. Let us take a tabular structure where I would talk about the mathematical area, what are the topics and tools required, and how do they connect to particle physics. First, obviously, would come, that is the linear algebra. It deals with vector matrices, eigenvalues, and Hermitian operators. They definitely represent to particle physics in terms of quantum states, spin system, and symmetry operations. So second, obviously very basic, comes the differential and integral calculus, because this would be required in order to understand the evolution of space, the Klein-Gordon, Dirac equations, and a number of important concepts in particle physics. Complex numbers and functions, they form the heart of quantum physics and particle physics, obviously. So quantum wave functions and propagators are inherently complex. So Euler's formula, complex analytical functions, these are a very important topic and a mathematical prerequisites. As we turn the pages, we find that group theory and Lie algebras are very important, because commutators, SUN symmetries, these determine the fundamental interaction. So connection to particle physics in terms of group theory and Lie algebras are very, very important. You also need to understand the special theory of relativity and Lorentz transformation, because the four vectors Minkowski metric, the invariant property, also relate to what are called the Lorentz invariance, and physics must look at the same in all inertial frames of reference. So special relativity and Lorentz transformations are important. In the book that I would be talking about, you will see how special relativity has been reviewed. Quantum mechanics formalism, obviously, because commutators, expectation values, they pop up at every point of time. So from particles, as I showed, when we move in fields, quantum field theory, quantum mechanics, and the formalism is very, very important. Next, as we turn to the page, we find that probability and statistics also do play an important role, because expectation values, decay rates, cross-section, these are all related to probability and statistics. Obviously, Lagrangian and Hamiltonian formalism are related to particle physics, because it is central to what is called Dirac or Young-Mills or the Lagrangian density. It cannot be avoided. Finally, this is optional. You can have an understanding of differential geometry at a very, very basic level, because certain gauge fields or fiber bundles may demand a basic knowledge of differential geometry. Having said that, this actually covers our mathematical prerequisites. Now, when we go forward and select a book, whatever the book that you're selecting in due course of time of your career, what are the things that you should be present in a book, or what every particle physics learner should have a kind of a checklist before they purchase or select a book. Now, among many other things, I have selected few concepts. Number one, that the book should have these things which you can pause and read. The elementary particles, the standard model, quantum field theory, not in advance but the basics, experimental foundations, and certain concepts which are beyond the standard model. The book should have the basic mathematical requirements. That means linear algebra, special relativity, group theory, etc. should be there in the book. And you need to also check on the approach and style, because some books develop on historical context, some do not. So what is the concept? Is this conceptual or mathematical? Is it theoretical or experimental? So there should be a balance. It should neither be conceptual nor mathematical. It should not be only theoretical or experimental. There should be a proper balance between these two. I am telling all these things because in future, when you go ahead and select a book, learn a topic, develop a curriculum, maybe keep in mind that these are the checklists that you need to have before completing or making a book successful. The next important thing which most of the students I have seen they get confused is the level of audience. Well, you might be looking particle physics at an introductory level. So select or see whether the audience level of the book is introductory or intermediate or it is advanced. Because if your knowledge is at intermediate level, you cannot select an advanced book. If you are at an introductory level, you cannot select an intermediate level book. So the level of audience whom the book is targeted towards is very important to know. There should be certain additional features which are illustrations, diagram, Feynman graphs. Yes, these are very important, very central to any book on particle physics. And there should be exercises and reference to these experiments, the recent discoveries. Otherwise, you would be a dinosaur in today's age. So the quick tip that I would say is that a good particle physics book will develop and give you a roadmap from basic concept to modern developments without assuming you're already a quantum field theory expert. So you don't need to be a quantum field theory expert. You can just have a basic understanding of the basic concept to modern developments, and the book, a true good book, will assume that you do not have any concept of advanced quantum field theory. You're not an expert, and then it will go ahead and teach the book. Now, having said the mathematical prerequisites, what is particle physics, what are the steps, methods that you should follow, now I will talk about the first book that you can select, starting with, this is Robert Mann's An Introduction to Particle Physics and the Standard Model. Now, why I have selected this book has got several reasons. First of all, about this professor, great professor, Robert Mann. He basically works on gravitation, quantum physics, and the overlap between these two subjects. He is most importantly interested in questions that provide us with information about the foundations of physics, particularly those that could be tested by experiment. This is Professor Mann's University of Waterloo, the Google Scholar link, which you can go ahead and check his areas on development of physics, and he has already authored wonderful books. Now, before I go ahead and talk about the book, there is a note that you should be careful about, that whom this book is targeted. As I told you before selecting this book, the audience. So here the professor tells this book is for fourth year or senior undergraduate students to what is known as the standard model of particle physics. Now, when I say that is the fourth year or senior graduate students, that means the book assumes as it is underlined. You should have a good working knowledge of special relativity, quantum mechanics, and electromagnetism. From this basis, students who work through material will develop a solid command of this subject and a good working knowledge of the basics of particle physics. So I think this is quite modest, this is quite natural, that any book in particle physics will assume these three things: special relativity, quantum physics, and electromagnetism. So this is a kind of a notion that you should be knowing, and there are a few underlined lines in red which you can go, because Robert Mann found that particle physics is both mathematically and conceptually challenging, and in his 20 years career of teaching this subject, he has found that students can indeed rise to the challenge. And he tells that I have taken this approach in this book, beginning after reviewing relativity with some basic concepts in group theory and classical physics that lead to subject about symmetries, conservation laws, and particle classification. So this is a clear declaration from Professor Robert Mann, how he arranges, who are the people, and what are the basic mathematics that you need to have. We go forward and understand what are called the table of contents of this book, and as we go, we find that it starts with the introduction and overview. I'm not going to read each and every part because that would be lengthy and boring. You can pause the video and you can watch it if you want. So again, you can see there is a complete review of special relativity. So it starts with a relativity of simultaneity, time dilation, velocity addition, and so on. Next, the professor talks about symmetries, conservation laws, particle classification, and further as accelerators. So we come now to experimental physics, detectors, and so on. Further, if you go on the table of contents, you will see that scattering is covered quite a lot, where we have got this two-body rate, the two-body CM cross-section, etc. The toy theory higher order diagrams are being covered, wave equations of elementary particles, gauge invariance, and a part of QED is also being covered. Further, the testing of quantum electrodynamics through antiparticles matrix element from nuclei to quarks. The quark model is discussed, and the testing of the quark model. Then he discusses further about heavy quarks and quantum chromodynamics from beta decay to weak interactions and further. So here I would like to tell you the good part of this book is that along with the theoretical and the mathematical preparations, the book also continuously harps upon the discoveries, the accelerators, the experiments, and how these actually confirms with the theoretical predictions. Further, you can see electroweak symmetry breaking, testing electroweak theory, notations and conventions, and finally the Pauli and Dirac matrices with cross sections and decay rates concludes what is called the table of contents. Now, if I talk about the mathematics and the diagrams which this book particularly covers, then I would say that the mathematics is little bit rigorous, but it is not very rigorous as found in Peskin and Schroeder's book, yet more complete than pure conceptual text. So I can summarize that you can learn the equations as a tool for understanding, and it is mathematically rigorous but accessible. Here are few of the just the mathematical notations, just to let you know that these are the kind of mathematics which you will see, and this is written in clear notation, so you won't face any problem. If I talk of the diagrams, they are very well made. They are helpful figures, not much overcrowded. There are usage of labels, and Feynman diagrams are drawn very cleanly. These are few of the excerpts which I have taken from the book, and this is the way the diagrams are actually put up. From the mathematics and the diagrams, now we try to understand what is the methodology. That means how the book is organized, or rather when you go through learning this book, how do you learn this book all about? So if I talk of the methodology, the book starts with experimental foundation. Obviously, whatever we are learning in particle physics are being experimentally verified. So it starts with the methods, that means accelerators, detectors, precision experiments, how we know what we know. So that is important. Then it covers a brief kind of a review of special relativity. It builds on your four vectors, because particle physics indeed is built on relativistic kinematics. The symmetry based structure is also being covered, because this has been developed early on, and it is the conceptual heart of what is called the standard model. Further, the book on the fourth phase connects to the symmetry, that is the Noether's theorem, very importantly the particle classification. Then it goes forward on systematic particle classification, I mean to say how they are actually classified in terms of spin, angular momentum, etc. And then it moves into what is called from discrete symmetries to CPT. I hope you all understand what is the full form of CPT. If you want, you can put it on the what is called the comment box of this video. What do you mean by CPT? And then the book bridges theory with experiments. So here you can see the theory is already over here, right? We started with theory, and then once we connected theory with the experiment, so separate chapters are dedicated on accelerators and detectors, and then the scattering theory, which is a very, very important and the central tool which introduces cross sections, etc. And then it builds field theory from scratch, which is called the toy theory, and it goes further and further on. So this actually is the methodology, the way the book has been arranged, the way I would say your understanding of particle physics slowly builds on. And then finally comes what are called the wave equations, the gauge symmetry, and so on. Quantum electrodynamics finally is culminated, shows how quantum electrodynamics emerges from the gauge principles with a real world scattering example. Each of the chapter of this book ends with summary and certain questions, heavy use of examples, appendices, and calculations. This balances with conceptual clarity. So this covers the methodology part of the book, and now I would like to give you my overall review, the pros and cons, of the strengths and weaknesses of this book. So starting with the strengths, I would say it is an excellent bridge between undergraduate and graduate, because it explains advanced concepts like quantum field theory, etc. And I would also say that it is very clear and logical, because it explains the concepts and it designed for senior undergraduates, and it is a balanced emphasis between theory and experiment. So Professor Mann does not treat physics as pure abstraction, but he definitely goes back with real experimental evidence, what happens, etc. Here mathematics is not very rigorous or formal, but it is more complete than pure conceptual texts. If I talk about the weaknesses or the limitations, it assumes familiarity. I don't think it is a limitation. Any book of particles physics will be there. It is very dense in later chapters because gauge theories I found to be very dense, spontaneous symmetry breaking and so on. It has got limited problem sets, yes, because if you are concentrating on exercises, then compared to Griffiths or Hulsen and Martin, it is not an ideal book to look on practices and problems, and there is less intuitive storytelling. I mean to say, it can feel formal, very formal, because there is not very friendly compared to Griffiths and others. Having said that, I would like to conclude today's video on the first video on Introduction to Particle Physics and the Standard Model. However, there are a few more videos which are coming up in this series where I would be exploring, detailing and telling you about some very important and wonderful books on particle physics, so that your learning is not only on particle physics about the book review, but a kind of an overview on the concepts. So that's it for today's video. Thank you very much for watching this video. If you have liked, do not forget to subscribe to my channel Physics for Students and click and keep the bell icon ringing so that you get all the notification from Physics for Students. You can follow me on my Facebook and other social media handles where you will find some great and very interesting things other than the formal videos, and you can write to me at this email ID. Physics for Students will be soon back with more videos, and this series will continue. See you soon in the next video. But till then, goodbye, and may the good Lord be with you.